All right, we are live. So today I'm going to continue going through the practice problems. Um, Basically, as I mentioned before, kind of the practice problems is going to be kind of the new material for exam 3. I'm not going to ask anything that's not been covered in the practice problems. Obviously, everything in this course is cumulative, so things that were covered on exam 2 and 1 are also fair game. So in problem number 5, and again, the problem is specified by the page number, we're given a level control problem where H is equal to minus 10S V, which is the valve position. Again, this is the level in the tank, plus 1 over 10S, the inlet flow rate. So whenever I see a problem like this, the first thing I want to do is assign variables. So what's my controlled variable or output, right? That's my H of S. My manipulated variable or U is V of S, which is the valve stem position. And then my disturbance is the inlet flow rate, D. Likewise, I can also determine the transfer function. So my G is minus 10S or minus 1 all over 10S. So here G is a pure integrating process because we just have an S term here, and it has a negative gain. And we'll come back to that a little bit later. And then our disturbance transfer function is 1 over 10S, so it's also purely integrating. And then we're told that we have a controller with a gain of minus 1, so here's the minus part. And then our integral time is 1, so our controller transfer function just becomes minus S plus 1 all over S. And so then we're asked to calculate the closed loop transfer function. So starting with the set point transfer function, we get, here's the GC term, so we get S plus 1 all over 10S squared. So here we have the S plus 1, and then we're multiplying the 10S by S, so that gives us our 10S squared, and then the minus signs cancel out. So we get a positive number. And then that's 1 over S plus 1 all over 10S squared. And then when we multiply top and bottom by 10S squared, we get S plus 1 all over 10S squared plus S plus 1. And so that's your first transfer function. Disturbance transfer function, we have our disturbance D, right, which is 1 over 10S. And then we have 1 plus S plus 1 all over 10S squared. This is the GC part. Multiply top and bottom by 10S squared. We get S over 10S squared plus S plus 1. And so we're going to be asked to sketch the response for the disturbance, a unit disturbance response. And, whenever you do this, we got to look at the poles, right? And so we're looking at our characteristic polynomial for the closed loop transfer function, which is 10S squared plus S plus 1, right? And it's the same polynomial as the one down here, right? And, when we look at the poles, right, we're basically finding what are the roots of this quadratic equation. And if you plug this in, we get our minus b, minus 1 plus or minus b squared minus 4ac. A is 10 all over 2a. So we get this following formula. And this simplifies down to minus 1 plus or minus square root of minus 39 all over 20. I guess it doesn't really simplify down that much. But anyway, these are your poles. And the key part is, the real part is negative, right? So that tells us that we are stable, right? So we're going to converge to some steady state, and that we have an imaginary part, which tells us that we have oscillations. So now we can sketch the disturbance response. So if I come over here, again, my transfer function is D all over 1 plus GC, and that's S over 10S squared plus S plus 1. We know this polynomial is going to give us damped oscillations, and the S in the numerator tells us that the final steady state value is going to be 0. And so we'd expect our disturbance, a unit step response, is going to go up, and then we're going to have damped oscillations kind of converging. Now, this one's kind of complicated, so I don't really expect you to get the time scales for this, just that it's kind of a damped oscillation. Because all the numbers are positive, we'd expect it to go up and then down rather than down, then back up. And so this would be the response for a disturbance rejection, again, your damped oscillations. So the last part was, why was the gain negative? And so this is important. So whenever your gain of your transfer function, so if I come back here and I look at G, I have a negative gain here. And so in general, when you have a negative gain for G, you're also going to have a negative gain for your controller, so that way they cancel out. The other way I think about it is, normally when, in a kind of our canonical problem, when we increase the input, we increase the output. But when we have a negative gain, basically when we increase the input, we're actually decreasing the output. So our input was the valve position in H, the height, which are U and our Y. And because this is a negative relationship, we also want our gain to be negative. And that's kind of like a reverse acting controller. And so that kind of finishes problem number 5. All right, problem number 6, you're given the following system. So we've kind of seen this in homework before. So y is equal to 5 over s plus 3u plus 7 over s plus 4d. And we're asked to design a PI controller for this. And so the first thing we're going to do is get the g transfer function, this one right here, into standard form. So top and bottom by 3. So we get 5/3 all over s over 3 plus 1u plus 7 over s plus 4d. And so again, this is our g transfer function. And so if we look at the gain of this, it's 5/3, and our time constant is 1/3, which tells us that our PI gain is going to be the inverse of this, so 3/5, and our integral time is going to be the same, so it's going to be 1/3. So that tells us that our controller is going to be 3/5 s over 3 plus 1 all over s over 3. If I look at GC, 1 plus GC, just by design, it's going to be 1 over s over 3 plus 1. And our disturbance transfer function is going to be, this is the 1 over 1 plus GC part, so it's s over 3 all over s over 3 plus 1 times our disturbance transfer function, which is 7 over s plus 4. So you're first asked to do the disturbance transfer function. So if we look at this transfer function, we have a 0 in the numerator, right? And it's at 0. So that tells us that we're going to go to 0 at the very end. So that's our final value. All the numbers are positive, so we're going to go up. Our relative degree is 1, so no inflection. And we have 2 time constants. So we have a time constant of 1/3. And here we can think about this as a time constant of 1/4, right? Because I can rewrite this one as 7/4 s over 4 plus 1. And so if I look at the disturbance response, I expect to go up and then back down. And then roughly, the time scale of this response is going to be the sum of the time constants, which is 1/3 and 1/4. So that'll kind of give us an idea of what this response will look like. And then finally, our set point response, we have, we're going to have the gain of 1. That's the offset free part. And then, when we get to the 2/3 part, and I forgot to mark this down, we're going to be at 1/3, which is, again, our time constant right here. So that's kind of the solution for problem number 6. So problem number 7, basically we're given an unstable system. So this is y is equal to 1 over minus 2s plus 1. So this has a pole at positive 1/2. And then we're told we're given a controller with integral time of 1. So we have s plus 1 all over s. And we're asked to find kind of what range of proportional gains can we use. And so in this case, our g is 1 over minus 2s plus 1. And if we do gc all over 1 plus gc, so here's our g, here's our c, here's our g, here's our c. And when we simplify this down, we get kc s plus 1 all over kind of this mess at the bottom. And we can determine our poles, in which in this case, we're looking at that polynomial when we expand this polynomial out. So I'm just kind of expanding it out. You get minus 2s squared plus 1 plus ks plus kc is equal to 0. And there's just a general rule with quadratic polynomials that if all the coefficients are positive, the real part of the poles are going to be negative. So that's kind of just a rule, but we can actually see it here. So if we do the pole, we're going to get 1 plus kc plus or minus 1 plus kc squared plus 8kc all over 4. So the first thing we're going to notice is that we need 1 plus kc being less than 0, because this quantity here is never going to be negative, right? It can be imaginary, right? Or it can be positive, but it can't be negative. So we got to make sure this part is negative, so 1 plus kc is less than 0. And that's kind of basically it, which tells us that our controller gain has to be less than basically 1/2 or minus 1/2 for the system. So we have a negative gain, but it can go as negative as we want. And that's kind of the solution of this. And if you kind of just reason yourself through, you can see that if this is negative, then this term will be positive, but then k will be negative. So this will reduce this, and this will be less than this term. And so, or the other way is if basically, or one way to think about it, if all the coefficients of your quadratic polynomial have the same sign, I said it has to be positive, but we can multiply -1 across. If all of them have the same sign, then we know the real parts are going to be negative. And here we're forcing 1 plus kc to be negative and kc to be negative, right, which you can also see here. And if 1 plus kc is negative, then clearly kc itself is going to be negative. And that's where we get the condition kc is -1. Hopefully I explained that well. All right, so last problem. Basically, this is my sketch of it. You're told that you do a step input at 1 p.m. and your process goes from 4 to 12. And basically you're asked based on the step information to determine kind of the controller settings for this. So if you look at the information, our delta U is 2, our delta Y is 8, right? Because we're going from 4 to 12, and the delta U is in the problem statement. So K, which is just delta Y divided by delta U, that tells us that it's 4. And then from my reading of the graph, our time constant, where we get that 2/3 part over here, let me slide that over here. That 2/3 occurs roughly at 30 minutes. You know, basically, if you say anything less than an hour, it'd be correct. But, you know, it looks pretty reasonable at 30 minutes. And so putting this together, we get our G is equal to 4 over 30s plus 1. And basically, our gain is 4. Our time constant is 30. So this tells us that our controller gain should be 1/4 or 1 over k, and our interval time should be 30. And that's the end of the problem. So this one's kind of short and simple, but I kind of like these problems where you look at graphs and kind of back calculate out numbers from them. Anyway, if you have questions, please post them in the comments section. I'll do my best to answer them. I will put up later today information about the exam. And with that, stay safe and yeah, stay safe. See you guys later.